Welcome students. Today we are start with second chapter of material science, that solid solutions and diffusion in solids. Let us see introduction. We know solution is made up of solvent which dissolve the solute. The ability to dissolve is called solubility. Example of solid solutions are alloys. Solid solutions are homogeneous mixture of two or more kinds of atoms or metals occurring in solid state. In the solid solution, there are two components. One is solvent and other is solute. The more abundant atomic form is called as solvent and less abundant atomic form is called as solute. The amount of solute dissolved by solvent is depend on temperature. There are two types of solid solutions. First type is substitutional solid solution. In this type of solution, atoms of solvent are replaced in crystal lattice by atoms of solute. For example, copper atoms substitute nickel atoms without disturbing FCC structure of the nickel. Figure shows types of substitutional solid solutions. As shown in the figure, diagram B and diagram C shows two types of substitutional solid solution, that are ordered substitutional solid solution, where solute atoms have substituted solvent atoms on their lattice side in ordered manner, and second type is disordered substitutional solid solution. Here solute atoms substitute the solvent atoms on their lattice side in disordered manner. Second type of solid solution is interstitial solid solution. In this type, solute atom doesn't displace a solvent atom, but it enters one of the holes or interstices between the solvent atoms. It has higher density than substitutional type solid solutions. As shown in the diagram, in iron carbon system, carbon are the solute atoms occupies an interstitial position between iron, which are solvent atoms. Atoms having radii less than 1 angstrom make the interstitial solid solution. For example, atoms of carbon, nitrogen, hydrogen, oxygen, etc. can form interstitial solid solutions. For these solid solutions, there are some rules. First, we see Hume-Rothery rule for substitutional solid solutions. According to this rule, formation of substitutional solid solution between two metals is governed by set of rules known as Hume-Rothery rule. According to this rule, first factor which affects the solubility of solid solution is atomic size. Size difference between the atoms of solute and parent metal should be less than 50%. It means the atomic diameters of both solute and solvent have difference less than 50%. Second factor is crystal structure. The crystal structure of solute and solvent must be same. Third is valency. For complete solubility, valency of solute and solvent must be same. Next we see what is the atomic size factor. If the difference between atomic diameter of solute and solvent atoms is more than 50%, then solute solubility in the solvent is small, so the extent of primary solid solution is small. For complete solid solubility, the size factor must be less than 8%. If the atomic diameter of solute and solvent differ by more than 50%, then size factor is unfavorable and solid solubility is small. Next law for solid solution is Figaud's law. It gives empirical relationship which states that the lattice parameter of a solid solution of two constituent is approximately equal to a rule of mixture of two constituents lattice parameter at same temperature. Consider two components A and B. Out of A and B components, one is solute and other is solvent. When A and B, that is solute and solvent, combines, we get resultant solution denoted by capital letter C. All this process happen at a constant temperature T. In the equation, AC is the lattice parameter of C crystal. A0 is equal to lattice parameter of pure A component. AB0 is the lattice parameter of pure component B. X and A minus X are the concentration of B and A respectively in the mixture, which are nothing but the mole fractions of components B and A respectively. From this equation, we can conclude that lattice parameter of solid solution is the linear combination of two components. This is useful in practice to obtain rough estimates when experimental data are not available for lattice parameter for system of interest.